what I want to go through is the check of this. Now, when we check this, it might actually be more work than what it took to actually do the question. But it's work that we've done, okay? It's an ability that we should have. So as we go through this, we're going to be talking about that angle and that angle. Those angles are going to tell us everything we need to know about phi and theta, right? Okay? So if I want to check to see if this thing here is the right answer, then I need to know what those two things are. Because if I know what theta and phi are, if I know what they are numerically, can't I just take cosine of those two things subtracted, get a decimal, and see then if that decimal is equal to what I got a box around up there? Okay? So with these pictures, we have that ability because we understand and we know that when I have cosine of theta and gives me this picture, then I should be able to take arc cosine of 8/17, and that actually tell me what theta is, can't I? Does that make sense, everybody? And I can also, and I could, because I have all three sides, I could actually use arc sine, arc tangent, arc secant, arc cosecant, whichever one I want to use. Okay? But I should be able to do the same thing over here for phi. I should be able to say, I'll use tangent just to kind of show you a situation that occurs. I can use tangent inverse or arc tangent of negative root 15, and that should tell me what phi is. So I'm going to grab our calculator. And I'm going to, just because it makes things just simpler, I'm going to do everything in degrees here. But if I figure out what arc cosine is, 8 divided by 17, it gives me 61.9, right? Now think about this. Is theta 61.9 degrees? No. The blue angle is 61.9 degrees. Theta, how do I find theta? 360 minus that. Good. So there's theta, 298. Okay. Let's do arc tangent of negative square root of 15. See what that looks like. Negative 75. Is this angle phi, is that negative 75? No. Negative 75 should be the scale's not great here, but negative 75 should be that angle there. Does that make sense, everybody? Okay. What do you know then? If that's negative 75 degrees, and negative just tells me the direction, if that's negative 75, what's this blue angle? 75. Those two angles are vertical, aren't they? Okay. So how do I find phi then? If this blue one's 75 degrees. Yeah, stretch from 180. So I'm going to go 180. Subtract from it that number there, and I get 104.47. There's phi. So can't I take cosine? So I know now know what theta is. Theta was this 298 number. So let's cut that out. Put it there. Minus then phi, which is that number, and gives me negative 0.97, right? So there's the decimal of cosine theta minus cosine phi. If I take negative 8 minus 15 square root of 15 divided by 68, does it give me the same decimal? Okay. So now that took some time, right? And ultimately that takes probably more time than what setting up the original problem did. But if I've got time on a test or a quiz, if I'm just sitting there and I'm done with the assignment or whatever, or I'm at home and I got time and I want to be sure that I type the right answer in, or I'm on the ACT or whatever, and something like this shows up in one of those last 5 or 6 questions in the ACT, it'd be nice to have the ability to check to see if I've done things right. Okay. So, 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 in addition to not only checking, but it does kind of solidify and sharpen those skills that we need to eventually address what ends up being this example 7 here. Okay, we'll cover here in a little bit. All right, that takes us to just basically today. All we're going to do is some examples, but this one kind of takes a little bit of time because we're going to do it 2 different ways. Because right now we haven't, I've shown it to you, you maybe written it down, but we haven't really proven the tangent sum or difference formula. So I don't want to use the tangent sum or difference formula because I want to show you the benefit first of having it. So that being said, and understand what our formulas do for us, they are things that should provide efficiency, right? Okay. They are developed usually because we see a process occur over and over and over and over again, and it's a pattern process, and it's kind of an elongated process. It's difficult, okay? Can we develop a formula to kind of circumvent the process and still get the same answer, okay? So I want to see if we can do that here. So if I take tangent, and I want to find tangent of 17 pi over 12, so that is a multiple of 15 degrees because of that denominator of 12. And we, for the most part, probably don't know what that is off the unit circle. So I'm going to write this way. I'm going to say sine of 17 pi over 12 divided by cosine of 17 pi over 12. Okay? Now and I think this is probably a fair statement for everybody. If I ask you to figure out off the unit circle what angles that have a denominator of 4 and 3 or 6, which combination of those will either add or subtract between 17 pi or 12, that's going to take a little bit of effort, isn't it? Okay, take a little bit of time. So the best thing to do is to take this 17 pi over 12 and multiply it by 180 over pi, right? And if I do that, 255 degrees. Is that easier to think about than 17 pi over 12? Yeah, okay. So I have sine of 255 over cosine of 255. Now, does anybody know what the sine value of 255 is? No. Okay, it's not all in the unit circle, right? If we bring up the unit circle, 255 is not there. Okay? But by using some of the values that are off the unit circle, I'm just looking at these orange degrees right now. Can I take a couple of those down together? Could I take those two down together, get 255? Can I take those two down together, get 255? Can I take that one and subtract them to get 255? Okay. So what I want you to see here and realize is that you might be a person that uses 120, 135. Your neighbor might subtract and use 345. But you should both get the same answer. Does that make sense? Okay. I'm going to use 120, 135. Okay. That's what we used last class. And throughout this process, we went through it, and then I was stupid and deleted everything real fast for them, and they didn't have a chance to copy down. So I told them I would do it the exact same way in this class, but not delete it real fast, so they can watch it and copy it back down. So I'm going to write it that way. Okay? Because now I've turned 255 into a sum, and we now know that this set of sums can be rewritten as the sine, because the numerator is sine, so it's a sine of a sum, so it's going to go sine, cosine, same sign, cosine, sine. The denominator is a cosine, so it's going to go cosine, cosine. I've been saying cosine, like complementary sign or opposite sign, and then it goes sine, sine. And once we have that kind of general format or template down for these sum formulas, what they look like, now I just go back in and take 120, 135, and up here I just plug in them in that order, 120, 135, 120, 135. Same thing on the bottom, it was 120, 135, so I'll go 120, 135, 120, 135. Now, here's the thing. We could, when we do this, stop after we evaluate and it gets to be a really ugly fraction and just say, yeah, we're done. But when we evaluate something, kind of what's in the back of our mind every time we evaluate something is we want to make it as simple as possible, right? Okay. And if I evaluate a problem, I get down to 3/9, I want to make sure that I change up to 1/3. So that's going to happen. There's going to be some ugly stuff going on here. And there's going to be some algebra that we have to use here to help us simplify, rationalize, all that kind of stuff. Okay. But evaluating these, we should know what sine of 120 is. Okay, going off the unit circle, the y value at 120 should be what? Radical 3/2. Okay. The cosine of 135, what's the cosine of 135? Radical 2/2, but make sure you know it's in the second quadrant, so it's got to be negative, right? Okay. Plus then, cosine of 120. Cosine of 120 is negative 1/2. And then sine of 135, sine of 135 is radical 2/2. So that's my numerator. Now, what's nice about this, at least in this situation, is that these on the bottom are already values that we've evaluated. We just got to make sure we got them in the right order. So cosine of 120 would have been this negative 1/2, right? So negative 1/2. Cosine of 135, we said that that was the second one, so it's negative radical 2/2. Minus then sine of 120. Sine of 120 was the first one, so radical 3/2. And then sine of 135 would have been radical 2/2. Okay? All right, so we got some multiplication to do. Negative radical 6 over 4. Negative radical 2 over 4. I'm just going to write it. Since the denominators are all going to be 4, right? Can I go ahead and do that algebra of where I add the numerators together? So negative radical 6, this gives me negative radical 2, and they're all over 4, so I use that as common denominator. Now, on the bottom, I'll have negative 1 times negative radical 2, so that's radical 2. It'll be over 4 again. And then this one's going to be, what, minus radical 6? So we got a fraction divided by a fraction, right? When you have a fraction divided by a fraction, you do multiply by reciprocal. Now, this is one kind of interesting situation. I don't know if we've talked about this before. But if those denominators are the same, you can actually just, what you're going to get is that divided by that. Okay, if you go through the process. So I'm just going to write that down. Negative radical 6 minus radical 2 all over radical 2 minus radical 6. Now that's a lot better than what this blue stuff was, but it's still not kind of a preferred method because we don't really like ever having radicals in the bottom, right? So we're going to go through the process of rationalizing that. Rationalizing means take an irrational number and through multiplication make it rational. Okay? So how do I do that here? Remember? Multiply by the conjugate. Good. Okay. If I multiply by the same thing, if I multiply, because that's what we do with radicals when it's not a sum or difference in the bottom. Like say I just had divided by like radical 7, I'd multiply the bottom and the top by radical 7, right? And that will rationalize. If I did that here, it's going to be okay. It will rationalize the radical 2 when I do first times first. It'll rationalize the radical 7 when I do last times last. But when I do O and I, it's going to give me like radical 12 multiple times. So it won't rationalize that. Does that make sense? So that's why we can't multiply by the same thing. We have to multiply by the conjugate. Because by definition of a conjugate, through the multiplication, don't O and I become additive inverses? They cancel each other out. So when I multiply on the bottom, I get radical 2 times radical 2, which is just 2. And it's going to be minus radical 6 times radical 6 is 6. Did that rationalize? Did you take this irrational number and get a rational number? Okay. Now up here, it's a little bit more work up here because they're not going to cancel. Okay, O and I. So we gotta multiply. We get negative or FOIL here, I guess, which is multiplying, but let's give myself a little bit more room here. When I multiply negative radical 6 times radical 2, I get negative radical 12. Negative radical 6 times radical 6 gives me negative 6. Negative radical 2 times radical 2 gives me negative 2, right? And then negative radical 2 times radical 6 gives me negative radical 12 again. Okay. So that ends up being, what is radical 12 the same as if I rationalize that? 2 radical 3. So that's negative 2 radical 3 there. This is another negative 2 radical 3, right? So that means that my numerator becomes negative 4 radical 3 negative 4 radical 3 minus 8, right? Is there a common factor of negative 4 in all of those? So they're going to cancel there. Leaves me just radical 3. And then negative 8 divided by negative 4 gives me positive 2. That's a pretty clean looking answer based off what we started with, right? Okay. Let's see if we've done things right. Should be able to take tangent. I gotta make sure my mode is in radians here, but tangent 17 pi over 12, and it gives me 3.73. Now, hopefully, maybe you automatically know then what you came up with the radical 3 plus 2 is right. See, we know what radical 3 is as a decimal or approximately 1.73. Add 2 to that, don't we get the same value? Okay. Now, would you want to do that? Let's say that we're in a homework assignment and we've got 5 or 6 of these back to back. Do you want to do that 5 times? No, absolutely not. Okay. So let's see if we can go through the same process, but instead of calling this 120 and 135, let's call it like S and T or A and B and see what happens as we go through. So see if we can generate a process here that will quicken this. Okay. Am I okay with deleting that word? All right, so I'm actually going to go to a blank page here, and we're going to take so we had tangent. Let's just use just stay consistent. S and T. I'm going through what we just did. That's sine of S plus T divided by cosine of S plus T. Now I'm just going to expand those using the sine sum formula and the cosine sum formula. So it becomes sine of S cosine of T plus cosine of S sine of T. And on the bottom, it becomes cosine of S cosine T minus sine S sine T. Okay? Now, the next step, and you might not recognize this, but and why we do this, it's just by sitting and looking at this for a while and saying, okay, what can we do? What algebra can we do to maybe make this a little bit simpler? What algebra can we do? Because if we think about the sine and cosine sum and difference formulas, they are in terms of sine and cosine when we expand them. So when we have a tangent sum or difference formula, it would be nice if it was in forms of tangent when we expand it. Does that make sense? So we sit and we look at that thing and say, okay, how can I get tangent to show up? Okay? And what happens is if we recognize this thing right here, this term, we should put print or quotations around it. If we recognize that term right there, and we go through and divide every single product up there by that term, some really nice things are going to happen. Okay? So what I'm going to do is, just so that we're able to see all of this real nice and the way things cancel out, I'm going to rewrite that numerator, but I'm going to give myself some room so I can put in a denominator. So I'll kind of just write it out, and then you'll see what I'm talking about. So I'm going to give myself room to divide each one of these by something. And then we'll do the same thing on the bottom. So cosine of S, cosine of T, minus sine of S, sine of T. And now I'm going to take this thing here, and I'm going to divide everything by it. So it should look like cosine S, cosine T, cosine S, cosine T. And obviously, you know, it gets pretty ugly. But if you sit back and you think about it, some really nice things happen here. Okay? One of the nice things that happens is that turns into what? It turns into 1. What does that turn into? 1. What does that turn into? 1. Okay. Now, we got a bunch of 1s there, but what does that become? Tangent. And it's tangent of S, right? What does that become? Tangent of T. We now have a 1 here. Okay. Now these 1s, they got multiplied through by a tangent S and a tangent T, right? But this is a complete, nothing left over to multiply, so it is 1. What's this thing here become? Tangent. It was a minus sign here. What does this last one become? Tangent T. So now we have tangent of S plus T. And just by replacing T with negative T, we will see that this thing transforms to tangent of S minus tangent of T over 1 plus tangent S tangent T if you need to subtract your angles. Is that right? Now, what's the benefit of that? Now, if I want to find the tangent of 255, okay, let's do this real quick, and I'm just going to, you might have to rewrite it, but I'm going to just remove this, and now say, if we're doing tangent of 255, that's 120 plus 135 again. So now I'm going to take tangent of 120. This is going to be tangent of 135. This S will become 120, and this T will become 135. Okay? Now, there is a cost to using this formula, okay? Because when we expanded it in sine and cosine, we have the unit circle memorized for sine and cosine, right? Or we should, okay? We don't have those for tangent. We haven't memorized those because we know that we can find them quickly. If I look at my unit circle for just 120, okay, and do sine divided by cosine, what's radical 3 over 2 divided by negative 1/2? What's going to happen there? 2 is canceling, left with negative radical 3, right? So tangent of 120 is negative radical 3. Tangent of 135, what's the tangent of 135 if I divide those out? Negative 1, okay? So now we can evaluate this. We can now say that this is equal to tangent of 120, we just said was negative radical 3, right? Tangent of 135 is negative 1. Tangent of 120 again, negative radical 3. Tangent 135, negative 1. Now we should be able to take this and simplify a little bit further. Negative radical 3 minus 1. This becomes 1. Now that's going to become positive radical 3, right? But it's now minus a positive radical 3. And now we get to the stage where we still have radicals in the bottom, right? So we rationalize. Multiply by the conjugate. Now, what happens here is that this conjugate is a lot simpler than the one that we multiplied earlier when we used sine over cosine, right? Okay. These values here that we evaluated and determined, these are smaller values, easier values to deal with than what they were when we left it as sine of 120 over plus 135 over cosine of 120 plus 135. So now if I rationalize here, 1 times 1 gives me 1. Radical 3 times radical 3 gives me minus 3. Up top, okay, now these are not conjugates, so you actually have to do the foiling. Negative radical 3 times 1 is negative radical 3. Negative radical 3 times radical 3 is minus 3. Negative 1 times negative 1 is, or negative 1 times positive 1 is negative 1. And then negative 1 times radical 3, negative radical 3. Rewrite it up here now. What's negative radical 3 minus radical 3? Negative 2 radical 3. What's negative 3 minus 1? Negative 4. 1 minus 3. Negative 2. These all have a factor of negative 2 in them now. Factor that negative 2 out. Gives me radical 3. Factor that negative 2 out. Gives me plus 2. Okay. It is a quick, if you sit down and you try to do them side by side, put a timer on yourself, it is quicker using that formula instead of sine or cosine. But the cost of that is, obviously, you're going to have to evaluate at tangent of your unit circle values, which you might have to kind of quickly come up with on the side. shouldn't be something extremely difficult to do, but that is an example of how to use that tangent sum or difference formula. Is that okay? Okay. Now you would come up with the same answer if you would have taken tangent of 300 minus 45. Okay. That still gives you a sum of 255. All right, so on here, just again for the sake of time and essentially because we've already done it, I'm not going to do example 6 with you. Okay, you would expand this to sine x cosine pi over 2 minus cosine x sine pi over 2. But the nice thing about these is whenever we're dealing with this pi over 2 and we're using sine and cosine, that's either going to generate zeros and ones, right? Okay. Well, that ends up being really nice because either a product is going to disappear or a product is just going to become something times 1. That question, that example is exactly the same thing as we did up here in example 3, using a different argument and a different, we start here, and example 6 was sine, but you should be able to do the exact same thing you did here in example 6. Does that kind of make sense, everybody? So those are very similar questions. I want to do example 7 because it's a version of that, but a little bit more difficult. I'm going to make the statement, because I didn't write this in the example when I wrote this out. Let's just say that all of these angles that we're going to deal with exist in the first quadrant. It just makes things a little bit easier. This is a really ugly way of them telling you you have the cosine of an angle minus an angle. Okay, maybe we call those angles I don't know, alpha and beta. Okay, if I had so they're saying this is their way of implying what alpha is. This is their way of implying what beta is. Because every time I use sine inverse or tangent inverse, the input value is a ratio, right? The input value is a ratio. That's what our domain is for those things. And the output value is then an angle, correct? So the input here is x. The sine inverse of x. That should be producing an output of an angle. Okay? What we're going to do here is the idea is if, you know, maybe we got 5 or 6 of these problems to do back to back. Okay? And x and y are going to vary. Okay? Maybe x becomes, in one question, it's pi over 3, and then y is pi over 6. And then in the next question, x is pi over 4, and y is I don't know, pi over 12 or something like that. Okay? And we would have to go through a really, really, really long, elaborate process to do each one of those questions. So what we're going to do is we're going to do this process with generic x's and y's and see what we developed. And that formula that we developed should be something that will allow us to quickly reproduce answers based off varying x's and y's. Kind of like when you guys were in Algebra 1 or 2 and you did the completing the square. Completing the square is a long, arduous process, right? But then we say, okay, well, let's just take ax squared plus bx plus c equals 0 and complete the square with that. And we complete the square with that, it gives us the what? Quadratic formula. Okay? And then the quadratic formula will quickly do the complete the square process to anything that we want it to, right? So that's what we're going to do here. These are types of questions that, like the end of the ACT. I don't know if the ACT will get to this difficult of a problem, but these are types of things that the last 4 or 5 questions on the ACT would kind of address. Okay, so when they give me this information, they're telling me an angle, but I don't know what that angle is yet. I have to kind of mess around with it. So this is what we're going to do. I'm going to draw a picture. And now, like I said, I'm going to assume that everything is in the first quadrant here. So this here would be our alpha. That's the angle that they're describing information about here. Okay? Remember, so this here is an angle. Okay? But the input here, this x, is our ratio, right? When we say ratio, that's the division of two things through, or sorry, the comparison of two things through division. Said that backwards. So what's the denominator here? It's 1. So now sine inverse of our ratio, well, sine is opposite over hypotenuse, isn't it? So you see there they gave you all the information you need to know about this angle alpha? Because now, if that's alpha, if this is x and this is 1, it's a right triangle, we should be able to go through the Pythagorean theorem. We'll call this side A. Once you guys agree that a squared plus x squared is equal to 1 squared, and then a would be 1 minus x squared, and obviously we take square root. So our adjacent side here, and you'll see why we need to do that here in a moment. Our adjacent side, there would be 1 minus x squared under the square root. And that's alpha. I want to do the same thing now for beta. So again, I'm going to assume beta is in the first quadrant and be that angle there. Tangent of y, that's y over 1. Tangent is opposite over adjacent, right? Can we use the Pythagorean theorem? It's a lot quicker here. Can I say 1 squared plus y squared? And then we take the square root to find that distance. So now I know everything about beta. So when they ask me this question here, okay, when they start me off with this here, we know that's saying cosine of an angle minus an angle. One of those angles, we've defined them as alpha minus beta. So now let's take cosine of alpha minus beta. Let's expand that. It becomes cosine of alpha, cosine of beta. It's going to be plus then sine of alpha, sine of beta, right? Now, why do we have to draw the pictures? Because don't the pictures tell us what cosine of alpha is? Cosine alpha is root 1 minus x squared over 1, isn't it? Cosine of beta is 1 over 1 plus y squared under the root. Plus then sine of alpha, sine is opposite over hypotenuse. Times in sine of beta, which is y over 1 plus y squared. Now these are all going to give me, so if I look at these two fractions, that fraction there and that one there, they're going to have the same denominator, right? Numerators are going to be, that product and then that product. So I'm going to rewrite this as xy plus 1 minus x squared. And now I have solutions or a formula to find variant solutions. So if they ever ask me, like, what is the cosine of sine inverse, like I said, pi over 6 minus tangent of maybe pi over 3, now that's my x and that's my y. I can evaluate that and figure that out just by putting pi over 6 here, pi over 3 there, pi over 6 here, pi over 3 there, and evaluate. Does that make sense? Okay. And then the next question, say, okay, what if that's pi over 4 and that's pi over 3? Well, I could put pi over 4 here, pi over 3, pi over 4, pi over 3, evaluate, and I've got my answer. That kind of makes sense to everyone? Okay. Now that's how maybe you would check to see if you did this right. Okay. You can type in on like GeoGebra or Desmos or your TI-83 or 84, type in cosine sine inverse of pi over 4 minus tangent inverse of pi over 6. Hit enter, see what you get. Okay. Then in that formula, do the exact same thing with the exact same x's and y's. Hit enter. They should equate. They should be the same. Okay. The only thing you got to pay attention to is that your x's and y's have to satisfy the domains for sine inverse and tangent inverse. Sine inverse domain is between negative pi over 2 and positive pi over 2, right? So you got to choose numbers that are in between there. Tangent inverse's domain is all real numbers, so that doesn't matter. Okay. When we have time during Wildcat time or third period, I will go through in the video and show how to check that with specific values. Okay. That's the idea. That's what math is all about. Going over process over process over process that is elongated, arduous processes. Can we make them simpler? Can we do it with arbitrary values and see if something generates that is simpler? And in this case, that would be that. Okay. I emailed you guys, and I forgot to tell first period this, but I emailed you guys. There's an assignment in your email that will be due next Wednesday. Just a couple of problems to simplify using your identities. All right, so I want to show you the benefit of being able to come up with this formula. Obviously, we talked about in class how we could, if I make this pi over 6, pi over 3, I should be able to plug those pi over 6 and pi over 3s over here and get a valid answer. Now, the only thing I got to make sure of, and I stated that at least here, you've got to make sure that we evaluate the sign between negative pi over 2 and pi over 2. But to make this work, right here, if we think about if x squared is smaller than 1, sorry, no, let's say bigger than 1, you're going to have a imaginary value of a square root of negative. So what we have to really do is make sure that this here is between, or this number here, x, is between negative 1 and 1, and I think we should be okay. Just because evaluating otherwise some other numbers like, if I tried pi over 2, and I'll show you here that that's going to be an undefined value. But we should be able to kind of replicate this. So let's see. I've just created on GeoGebra right now just sliders that change some values. So these are, if you want to think about it as our x's and y's at the last that are working. I can't use x and y's because GeoGebra will try to graph something. But so we had, I think it was cosine of sine inverse, so arc sine of x, and our x now is a, minus arctangent or tangent inverse of b. Okay, so I'll hit enter. It gives me that quantity with these a values and b values. And obviously I can change those to what I want, but you see that after I get beyond 1, it's undefined. Beyond negative 1, it's undefined. And kind of show you that way, that reason here in a moment. Those are whatever they want to be. All right, so let's do this. Let's go. I think it had x times y, so it would be a times b. Then plus, it was the square root of 1 minus x squared, which x squared is a. And we had that divided by the square root of 1 plus y squared, and y is b in this case. So I just want to double check real quick to make sure I got that correct. xy, so ab, plus square root of 1 minus x squared, divided by square root of 1 plus y squared, and y is b. Okay. So I should hit enter, and it should give me the same number, negative 0.49, and there we go. So you see that there's that formula, there's that formula. They are indeed giving the same quantity back, and no matter what value I plug in,
between, now, tangent, I can use any numbers I want to. And the logic is that your b value, go back to this, your b value, which is this y here, can be anything, because when I square it's going to be positive, add 1 to it, so it's going to be a positive number. So that's always going to be a positive number down here. We got to be careful here because I could have a negative there. So we see then anywhere between -1 and +1 for this thing, we should be good. Okay. Just to show you a little bit more here, going to a website that I'm aware of that does some neat stuff for us, just useful graphing and stuff like that, and evaluating. So I typed in the problem that we started with, and you see it just give us it's a multivariable kind of calculus. So plotting, it's not so easy. It's an implicit equation, that kind of thing. But this would be that what we call a 3D plot of that. Well, if I do the 3D plot of the simplified version, or I guess the version that we came up with xy plus 1 minus x squared square root of that over 1 plus y squared square root of that picture's the same. So there is that graphical approach to look at as well. But obviously GIA 384 is not going to graph this for you. I was even having trouble, and maybe, I'm not sure if this will, I'm having trouble with GIA, there it is. So we're getting that curvature, okay, and then when we type in x, y, time, or plus square root of 1 minus x squared, all of that divided by 1 minus, sorry, square root of 1 plus y squared, we see that the purple one, the red one, and the blue one, they're on top of each other. They're the same curve. So obviously, like I said, your TIA 384 won't do this, and I didn't even realize that I could do this with GeoGebra until just now. But you know, that's a surface that is created by that sine cosine stuff. You see here it's called a multivariable function, and you would investigate these types of things more in a Calc probably 3 class, and really analyze that surface. But you do see, you know, for our purposes, if I graphed off them, they are the same. So that tells us that we, by hand, algebraically, did all of this stuff correctly.